I'm happy to have a chance to talk with you this morning about air quality modeling and give you some ideas of where I think we're at in terms of air quality modeling and where we're going.
I want to start with the point that I think these are very exciting times in the sense that atmospheric composition is very important. We know that from air quality, health, environmental impact perspective. By growing awareness, I think within the communities, the civic community as well as the operational community and organizations, that atmospheric composition matters also to it and weather. And so this is a very exciting time as we think about how we can bring atmospheric composition, weather, and climate together to improve services. A couple of minutes talking about applications of atmospheric composition, but start with this slide. It's just one example, an example of the cascade of impacts associated with heat waves and air pollution episodes, which often occur simultaneously. So in blue, it's the kind of the meteorological and atmospheric composition state on heat waves, which is typically a stagnant condition of high air pollution levels. Then we follow the impacts down to society. The first level of impacts is from the side. Temperatures can impact the change expansion of railways. It causes rail disruption. It promotes disease vector growth. Certainly humans and animal discomfort from the high temperatures and humidity and air pollution. Stress public order as people get agitated and discouraged. Then all transport, this can propagate again to the cascade effect. Water restrictions, transportation blocks, spread of disease, animal distress, business interruption, service interrupted, and all down to the worst outcome of death, but increased illness, hospital, and then all sorts of economic components. So it really is. We sometimes forget about the decay that happens when environmental stress occurs. Course of atmospheric composition applications, we are probably most familiar with the air pollution modeling component associated with environmental protection, but I'm going to talk today about the growing importance of atmospheric composition in numerical weather prediction capabilities, and certainly atmospheric composition from both long greenhouse gases to short-lived climate pollutants such as black carbon have found impact on climate. And this notion that composition matters is more today than it has in the past. A couple examples here of exciting time, and I'm going to make this emphasis throughout the talk today that there's development in terms of development of air pollution models. I know in Korea you simultaneously are developing a new mesoscale meteorological model, and you're beginning to develop a new air quality model. So these are very exciting times in advancements. I know a couple examples here. We've done a lot of work, example in terms of looking at the sentiment play between meteorology and air quality, looking at heavy wintertime haze. We're beginning to flow in October. We'll begin the heating season in China, and then we expect in November, December, and January to experience meteorological conditions that are conducive to heavy haze. I'm going to talk about some results that we've been doing, looking at coupled atmosphere, the warp can fully coupled feed mode. And wintertime haze, what is shown here is a typical example of this is January 2010, 2013 were great examples. If you from the observational data, typically what happens in these high events is that you get very strong stagnation periods, so very low wind speeds, no more than 2 meters per second. At the same time, relative humidity is increasing. Flows are coming from the south. In this slide, very low boundary layer. We have pollution, low speeds, relative humidity increasing, so the pollution builds up. And find in the analysis of this, and our research and others show this, that secondary inorganic aerosol formation is very important. Helps about 70% of the mass. Also, not fully known chemical processes, really involves heterogeneous chemistry, and then feedbacks. The feed between the aerosol and the meteorology, when we take those feedbacks into account, it leads to shallower, lower mixing heights, so we trap pollution, we wind speed, and we also have a shift in the wind speed. So these things tend to amplify the severity of the ground level concentrations. Account for 50% of this feedback. One model, and we're beginning to understand some of the complexities of these feedbacks, and we're beginning to explain feedbacks in ways. The message I want to give today is that it's very complicated in terms of air quality modeling, and a single model, not that many different models out there, so we need to understand performance and understand that. So a very important activity that we're engaged with now is a model intercomparison study for Asia. Third phase, and maybe some of you are involved. I know there's several Korean research groups involved in this. We bring together the air quality models that are being used in the region to do a common experiment, and we're in our 25th year of this intercomparison, and this cycle is on just a prediction of air pollution in 2010 was our year in the experiment. And so that's topic one, just evaluating in a experimental mode where everybody uses the same missions and meteorology to begin their simulation, so we can come to models that's very difficult to do from just looking at isolated papers, so performance of the model. We also do emissions inventory certainly the Korean inventory people were very engaged in this process. And then topic three is focused on this feedback mechanisms between meteorology and evolution. So three different modes to this. The work of the experiment, we have 20 different laboratories involved, and these are the models that are used for air quality prediction in Asia. Forms of CMAC, this is a model developed in China at IP, Rackham, Workman, and there's a few other institute developed homegrown models. So, as a common inventory, we run under common set of experiments, we have common boundary conditions, and then we do a common set of analysis to really understand how models perform. Most of some papers have been submitted, but here's an example of why we need to do this. Here we're at comparison of surface ozone at 3 sites in Korea, and we're comparing it in China, Korea, Japan, South Asia. Again, there's this particular one is showing 9 models, and you can just spread. You see this is now a monthly mean seasonal cycle for 2010. And you had in the models gray, black dots are the observations, and you see this is a lot of red. Again, model run with a set of conditions. And a part of this model in comparison is understand what's driving these differences. Even though the model, it may have a different number of vertical levels, it may have distribute sort of emissions in different ways. And another interesting thing is that we have 4 different CMAC models and the same versions of CMAC. So theoretically, they're running the same grid, the model settings. The only thing different is the people running it and the computer they're running on. And again, it just points out that most of these models, CMAC and WorkChem, are still complicated models that require many inputs and many cells in terms of running models. So again, the point of this intercomparison is really understand this, but the message here is that and we expect to get a diversity of model predictions and has its own set of strengths and weaknesses. And so moving forward, just like in the weather prediction community, more we'll see ensemble predictions where multiple models to account for the variability. From just an example, in looking at the aerosol distribution, I don't want to belabor this. There's a lot of optical depth for the heavy haze, the winter period. So this is January of 2010. At the spread now in terms of so 2 NOx, CO, ozone from 2.5 and PM10. So again, you see, just again emphasizing the point that we have a diversity in results. The sorts of intercomparison studies allow the community. These are not about choosing the best model. It's to get modeling groups to understand in a common framework, strengths, weaknesses about the models, and also try to find where we have situations where no model performs well. This shines light on that particular area, and can we further develop the models. An example of that is coming up in the wintertime haze events. So the typical air composition in time haze in China, 2010, and it's the color code here, but I wanted you to look at sulfate. So in this event over the 4-day, 5-day period, we're going from about 50 micrograms per cubic meter to 400 micrograms per cubic meter. And that a lot of it is from this rapid buildup of sulfate, about 100 grams per cubic meter of sulfate over a multi-period. And all models that are running today produce that in the current off-the-shelf mode of calculations. They have chemistry, but there's no mechanism that is found its way into CMAC or WarpChem or any of these other models, and you can do that models underpick SO2. That actually led to a very exciting time. There's lots of papers being published now about what would be the mechanism that accounts for this observed buildup of sulfate over a few days, in cases just a few hours. And from our studies, and I'll show you what we published on this, we have found and speculated from my PhD student Gao's work that mechanism that was dependent upon NO2 with an aqueous phase chemistry and dependent upon relative humidity was necessary. So we proposed a conceptual mechanism that was needed. It shows the observations that are showing the rapid buildup of conversion as we go to higher and higher concentrations of aerosol. And at the same time, ozone decreases as the aerosol increases, but not to increase. So these are pieces of puzzle that led us to propose this. And then a group of laboratory and field experimentalists that had observations of Beijing air that we could look at and shine some light on this. But I don't want to go into the details, but we find a mechanism and develop a mechanism that looks at NO2 and can convert sulfate very rapidly if it's in aerosol water, the liquid layer around aerosols, if the pH is above about 5.5 to 6. So elevated pH, that reaction doesn't go, and then the reactions that are well known, and peroxide reactions are known, but they can't account for this rapid buildup. So we have proposed, published it, and there's just a lot of people looking to. Oops. Can I go back? So this is a science question now. The amount of water on fog droplets and aerosol droplets under these haze conditions, very measurement to make. What's each in that environment? The models are will simulate and very good at calculating those. But in this area was stimulated about years ago in the acid rain problem, and then has really been the focus of research for a while. But that is another message to the students here that there are hot topics that occur in science. We start for a short period of time, develop a lot of knowledge, and then kind of think we solved that problem, and then on to the next hot topic. And then and things are reflected in our models, but as back and we, like forward to this situation, and now we see that, well, our understanding wasn't complete. And so there's always this need for research, field observation, laboratory studies, and modeling studies to keep going on and improving understanding, which then can lead to improved predictability. Right now, kind of like there's a lot of models out there. models have strengths, they have some weaknesses. Models are being able to run with interactions with meteorology, but then that there's a diversity of models, and so that suggests that combining these models together is moving forward to improve predictability. Nothing I've shown you so far has actually optimally combined observations and models, and so I'm going to data simulation. So there are many ways we can use observations and models, and there's a whole spectrum of sophisticated ways of doing it. An example of a systematic way of doing it is a process called three-dimensional variational data simulation, and we're using this particular one called GI. So haze events in the winter are simulating AOD, but AOD retrievals are very difficult under these haze events, but also simultaneously simulating PM 2.5. And that in coupled systems. And why do that? Well, we're able then to better constrain the aerosol, which means theoretically that we're going to present the aerosol meteorological radiation interactions, which then could lead to reduced uncertainty in things like radiative forcing due to the aerosol, and that's an output here. An output is that we can obtain PM 2.5 distribution that then be used in assessments. And you know that. So this then is all the 5 sites that we used in the east side of the plane. The upper model is the model run WRF with no data assimilation versus the observed values, and the WRF is in the red, and these are kind of showing the distribution in these box diagrams. Using the forward model run, the model gets some of the variability, some of this data variability, but certainly doesn't have nearly as much of misses the peak values often, but doesn't have the same spread distribution than observed. Simulation, you see that the distributions predicted by the model are much better, and we have to better resolve these peak values. And then if you run, a health assessment impact by exposure using the model run, which is needed because you're going to get values at all grid levels. If you run this through a model of health outcomes versus better constrained distribution, you're going to get significantly different values. And this is we published that in Science Total Environment to indicate that one of the reasons, one of the motivations for optimally combining the reanalysis framework is to provide better assessment of exposure data for health outcomes. We need more data if we're going to be optimally combining measurements and models, and so very exciting times, and that's why we're here. This particular meeting is to move forward the progress leading towards future years where we're going to have a variety of observations from geostationary satellites. And one of the things that we're doing in these coupled modeling system is develop a simulation system that are able to make use of the instant information coming from stationary satellites. And so an example working with Jun Kim and his group assimilating AOD into the WRF-Chem environment. And then this for wavelength, but also by assimilating multiple wavelength information, you can get resolved change in terms of the aerosol distribution fields, and we demonstrated that as well. We published previously that has shown the value of this when we this new capability to existing observing systems. Do we get an improvement in predictability? And just an example, I'll just look at the bottom diagram. And this is the PM10 at the Korean sites for this. This is a 2012 case. After simulation, this is for a monthly for this time period of mean simulation of aerosol optical depth by MODIS only, which is a polar orbiting satellite. So we have information from each one time a day. Weeks improvement. This is fractional reduction. So any change in green to red is an improvement, but it's a fractional improvement of about 10%. When we add the GOSI, which has higher initial coverage, but more importantly, but as importantly, higher temporal coverage, so more likelihood of finding cells with cloud contamination, so more information the model can use to constrain its distribution. So we can very significant improvement when we're using the evolving data sets into model prediction. Out in the recent Q experiment where we have a whole bunch of enhanced surface observations, air observations, and supply so that we can further and improve these sorts of algorithms, the assimilation processes and models that are used for the assimilation. From a prediction standpoint, weather relies terminally on observation. There's millions of observations going into weather prediction every day. Not for and weather prediction results in the change of the initial state of the model. So assimilate data, we choose the initial conditions, and then run the forecast forward, and that works for weather. From perspective, the situation is a little bit different. So I can change my initial conditions for change my PM 2.5 initial state and then forward, but I lose information. The model performance will improve for maybe 12 hours, 20 hours, and then starts to degrade. And that's because air pollution is driven by sources and really dominating over the initial condition. So emissions are extremely important for good stability. So MUNT may be involved in developing emissions. It's typically done from very classical and important bottom-up perspective. The demand, what side of fuel we're using, what are the conditions of combustion, very old information goes into those. But that takes time, and typically the emission inventory available in 2017 is probably based on big data that was collected in 2013 or 14, so you have time lag between the emissions. So there is, from a prediction standpoint, there's a need to update emissions rapidly. Also, are very difficult to quantify emissions like fires, which are going. We have to know where they might occur. Can predict where thunderstorms might occur. We have to wait until we can detect that the fire is occurring before we can actually estimate the emissions, and it's highly uncertain. So there's a bit of development going on in terms of developing ways to use observations to constrain emissions. And as an example that we did in the NASA field experiment Seekers, we had a large aircraft DC-8 that based in Houston and flew here during a time period when a very large fire at, it's called the Ring Fire at Yosemite, and you see the fire burning here. It burned for a long time, and it was a massive fire, and the aircraft was able to come sample the fire and then follow the smoke plume as it transported towards the northeast, but in the northwest U.S., and the smoke ran and came this way, and so the airplane was able to follow it over a couple-day evolution of the smoke. Where we could use observations to rapidly constrain the smoke emissions. So I won't go into detail, but it's a variational method with a diagram here, but we can use spaceborne measurements, we can use ground measurements and airborne measurements. Any of those can be used to constrain the emissions. And we ended up with, for the rim fire, most of the time when in the modeling world, when we detect a fire, we estimate the fire from some satellite information that's based both on the hotness of the fire as well as some other information that shows the fire and the scar once the fire is over. and typically assume that the fires are a direct variation in the fires, that the fires are during the day and then they lay down so they simmer and they don't make as much emissions, and that happens over the duration of the fire. So this is an assumed profile. Well, through the process that we did, the end result was just using the satellite data and then adding aircraft data to it. We get a situation where we needed to increase the fire emissions during the day, but also increase that the fires were also more active during the night than anticipated by this assumption in the model. So at calculation, we have having to increase the fires substantially, and this is a change with the new emissions to the oceans. This is a change in PM 2.5 over a couple days average, and you can see that in the source area, the difference in PM 2.5 by cleaning the model led to more than 100 microgram per cubic meter increase in the smoke, affected the AOD significantly. And then in terms of the shortwave radiation, if you look carefully here, you'll see that there's changes where occur much in the smoke. Also, you see where differences here that are quite spiky. And that's in our model interaction. The aerosol is fed back through the microphysics, and so it's actually changing the cloud distributions, cloud formation downwind. Another example of wanting to use try time here. And so a couple talking about the impact of the aerosol on meteorology. So aerosol has this feedback. Drop is made with an aerosol, and so we've done some studies of putting smoke. And this is an example where this is in Central America during the late spring. The smoke is transported into the southern U.S. This is the aerosol optical depth that's by satellite. The flow is in this condition. It's into this area. And on this period in 2011, it was this smoke transported into a very unstable conditions where severe weather was occurring. Actually, 109 tornadoes occurred, and many of those were of the highest power. And the U.S. Weather Service predicted those, but current weather prediction models don't have a dynamic aerosol process in them. It's for tornadoes, but they weren't able to predict the intensity of the tornadoes. We've done calculations since that time where we redid the calculation where we had the aerosol coming in and the smoke interaction, and we were able to actually predict these higher intensities. So the black carbon from the smoke interacting with the clouds led to intensity of the tornado. Not the tornadoes, but an increased intensity. So just one example of the effects that can occur when we add aerosol to meteorology. I'm going to skip time. Further exploring this NASA field experiment that's taking place in Africa, where we're measuring during the burning season. These are all fires. This in this direction, and want to look at how the aerosol interacts with the cloud. And this is a schematic. As it comes off the continent, the aerosol is above cloud, and as we transport out in this direction, the aerosol settles into the cloud. And so we can look at various radiation effects with aerosols above cloud and then aerosols within cloud. I'm going to skip both these. The message I want to leave you with is that the meteorology certainly affects air quality. I think we know that. A couple slides just point out that atmospheric composition in weather. Certainly meteorology affects air quality, and it does it in a variety of ways. It changes the air temperature, and air temperature affects the reactions are temperature dependent. It affects which affects the advection distribution. Costs, of course, affect photochemistry, but also affect biogenic emissions from the surface. which many of those are dependent upon the amount of solar radiation. Affects the PBL height, certainly affects the mixing, the concentration profiles. Precipitation affects the removal of soluble materials in particles. Humidity, again, can affect the aerosol size and composition and water aerosol's ability to change the extinction, which affect high deposition. So the point is there's a whole host of meteorological contributions to air quality, and our ability to predict weather. We can't forget the fact. So if you're doing quality modeling, you know, the tendency is based on running CMAC or WARPM, and you're worried about the chemical prediction. The impact of the quality of the meteorology has as big an effect in most cases of air pollution as the meteorology and chemistry and everything else. So making sure that both need to evolve tremendously together. In terms of one area that's important is a better characterization of land surface. And the surface is important. That last slide shows soil moisture affects near surface temperature, which affects the layer development, which affects the biogenic emissions coming out of the models. And some recent study in this, and in this that I will leave here, we have some examples of that. So we need suitable land initialization, land assimilation, and really surface type in terms of the vegetation greenness factor, vegetation or urban development, because we have situations where land use is changing rapidly, places in the world where it's changing rapidly, and data sets upon which we use to characterize the model. You pick up the WARF model or the CMAC model and run with land surface. Those default land surface areas go back to the 70s. Okay? The world's changed a lot since the 70s, and so you can have a significant impact on your prediction. And I skip over this, but I've done some recent studies to look at, with a NASA field experiment again, to look at the importance of land initialization and the initialization process. We have a better initialization for the WARF calculation. In our case, you get marked improvement in surface temperature and in the prediction of the planetary boundary layer height. So this is a default way of doing it. These are the new ways of doing it with a longer land surface initialization, better land surface initialization. So, and to the way of doing things, the new way of alternative way of doing it with a better initialization, and compared to the aircraft estimate of the emissions out of a model for isoprene emissions. MEG is the model we use. We can match the observation. So again, there are ways of constraining emissions. Oftentimes, the physical state may be impacting the heaven of the emissions, and it's not just change of the emissions themselves from a mismatch perspective. Just other examples of what's going on from the physical state. Lightning happens under strong convection conditions. It produces nitrogen oxide. And all models that you're running or that you will run have options to do some sort of lightning estimate. Lightning, there's activity going on, for example, at US EPA, where they're now assimilating. There's lightning strike data. This is what the CMAC model in this particular case run with WARF would use this model. There's a significant difference, and so one approach is the lightning strike data. And how do you do that? Well, what they've taken is to when they observe lightning strike, the meteorological model to make it a storm. Okay, so the process-oriented approach to that, and when so limit the course of thunderstorm, and then not they keep it as clouds. And the point that these are the observed value of the lightning assimilation. They're able to reduce the bias in ozone prediction at 71% of the sites. So it's just an example of in the meteorological physical environment having also a profound impact on improving the prediction of something like ozone in this particular case. Giving you some examples, models are key to what we're doing in terms of air quality and composition matters from an air quality perspective. In air quality predictions itself requires, in some cases, improving the processes. So I gave you an example of the sulfur and aerosol. It also requires improvement in the emissions. Another of uncertainty. Although a point is it also requires the improvement in meteorology. And then this idea that it's not a one-way street where meteorology is done and then drives quality. Composition can also feed back and influence weather. And certainly from a perspective, the composition has a profound role to play. So next couple slides here on moving forward. Certainly models constrained with observations are really the key to today and the future. And moving forward, society, we need to go to higher resolution to address the needs. Combining quality meteorology together certainly increases the complexity of the system. It's need to improve the forward model itself, but also I gave you this notion from the model in comparison that multiple models are needed to really better predict the uncertainty and take that into account. And then this, it's not a model alone or any combination model can just on its own, but the relationship to and the need for the volume of the Earth observing system. It's observations, model, assimilation is that whole system needs to evolve. The global observing system and atmospheric composition is growing. The GEMS and the plan geostationary satellites focused on atmospheric composition, but the other sources, ground-based observations, certainly in Korea, China, are just great examples of super sites, sophisticated ground-based stations that are growing. More stations from aircraft observations, routine bases, both field experiments, but also on commercial aircraft. All of this is evolving our capability to better the environment. And a game changer from both the scientific and the citizen engagement is this kind of the explosion in terms of the law sensors and our ability will be how can we make use of this emerging set of different quality of observation. And so the models constrained with observations are playing an increasingly important role. And a lot of activity going on now in terms of bringing together at both the research community and at operational centers to bring kind of atmospheric composition, weather, and climate services under one organization and to do what's called this seamless prediction across scales. And that's exciting and challenging. And it's certainly the highest level of the high-level strategy within the World Meteorological Organization from a research and operational perspective. It points out the reason for doing this is that we have air quality, weather, climate variability, and signals for both climate and air quality moving forward. And we have this growing need to extend capabilities of predictions from casting air quality components into to sub-seasonal predictions and then to climate services where we're looking days in advance. And is that this is really stimulating really exciting model development, both meteorological and air perspective. Many centers, and I mentioned at the beginning that Korea is one of those, and they lead to things like single grids no longer need to do any sort of nesting. Your global model, and you're able to a single grid system with the same computational resources, but you can refine the grid instead of a nesting for CMAC for the continental U.S., just refine the grid so that you have higher resolution occurring over the region. So I think I'll stop. Thank you.
Well, 3 minutes we were